So we're talking about sine x and its Maclaurin polynomial, sine x. We say is approximately equal to this Maclaurin polynomial, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, et cetera, et cetera, et cetera. Okay, and we say this Maclaurin polynomial here, I'm just going to use 4 terms, okay, will do a very good job approximating sine around where we're centering things. And we're centering things around 0, right? So it's like the closer we are to 0 that we plug in the sine, and the closer we are to 0 here that we plug in, the more accurate our approximation becomes, right? Then the question becomes, what if we continue to add terms? What happens? Well, we always talk about these, we've talked about these Taylor polynomials doing a very good job of approximating what's going on at the function where we are centering things, okay? And, we started with just some random function centered at here, and we said, well, at least we know that if we match first, second, third derivatives, that we're going to be, doing a good job right there, and we'll start seeing curves that do a better and better job, but, maybe we'll just follow it along even better. But then when we start adding terms, we notice something interesting. Now I'm going to graph sine and then just 4 terms of its Taylor polynomial. And I see, right around 0, we do a very good job of approximating sine. We are following the curve of sine better and better and better, very well around 0. But when I add terms, what ends up happening, and I went to x to the 25th, is that I don't see a difference, and I'm going all the way out to like 9 and to 10. It's negative 9.3 and 9.3. And I don't see a difference between the sine graph and the purple graph, which is the Maclaurin polynomial that is used to approximate sine around 0. And I'm talking about all the way over here and all the way over here. What do you think this means? Okay? If something is infinitely close, essentially they are the same thing. What do you think it means? The series, the infinite sum, this Maclaurin series, will converge to this function, which means the Maclaurin series for sine is equal to sine of x. They are one in of itself, the same. Now this is crazy, and I go through a lot of kind of different stuff showing you that fact that it is converging, this infinite sum, and we are not talking about polynomials anymore. Let's change up and we'll talk about the series. We're talking about these Maclaurin series, which are the infinite sum. And we should remember the ratio test, and I go through kind of in your notes, reminding you about the ratio test and intervals of convergence. And then we go into, and this is the second one we did, we go into sine. Okay, and I said, okay, well, sine is approximately going to equal this Taylor polynomial is going to do a good job approximating sine. But then I said, well, what if we look at the series, not the polynomial, the series, and I look at an infinite amount of terms. Okay, well, I look at the convergence of the series and notices that no matter what the x is, this series will converge. Okay, no matter what x is, you can plug any x into this infinite sum and you will get a number. Plug in any x. Okay, and what we can see graphically is that the numbers that they converge to are going to be equal to the sine values. And what we can now say is that just kind of by graphically inspecting and also kind of looking at the ratio test to show that it's convergence, that sine is not going to be approximated by the Taylor polynomial and approximated by the Taylor series, the Maclaurin series. Sine equals its Taylor series. If you look at an infinite amount of terms, this polynomial, that's what's fascinating about these things, is that they're polynomials. They're just using x to a powers. This polynomial will give you every single exact value of sine. So it doesn't matter if we're talking about the sine of 3 or the sine of 300 or the sine of 300,000. The sine of 300, even though you might have no idea what it is, a lot of mathematicians did not know. It's like, how do I express a right triangle with an angle of 300? And like, where is that located relative to 2 pi? And how do I know the ratio of its sides? Instead, they're like, well, I know the sine of 300 equals 300 minus 300 cubed over 3 factorial plus 300 to the 5th over 5 factorial minus 300 to the 7th over 7 factorial, et cetera, et cetera, et cetera. As long as you have an infinite amount of terms, they will equal each other. This should be kind of blowing your mind because we talked about things being good around the center, right? The center is at 0. 300's relatively far away from 0. However, our Maclaurin polynomial, with just focused at 0, does such a good job that as we continue to add terms, it fits the graph of sine. And the Maclaurin polynomial turns into sine. And we now have this equality. Okay? Same thing can be shown for e to the x. We go to e to the x, we realize it converges for all of its values. And though we say e to the x is approximated by its Maclaurin polynomial around x equals 0, and we can use the Maclaurin polynomial around x equals 0 to approximate values of e to the x. No, turns out e to the x equals its Maclaurin series. So e to the 3rd or e to the 30th or e to the 300th, you can use the Maclaurin polynomial. This is something centered at 0, but using an infinite amount of terms, we start to fit further and further out to the left and to the right of the graph of e to the x. And we can say e to the 300 is just equal to 1 plus 300 plus 300 squared over 2 factorial plus 300 cubed over 3 factorial, so long as you use an infinite amount of terms. Okay? And approaches infinity. The same can be done for cosine. The cosine function is equal to its Maclaurin polynomial. If you use an infinite amount of terms, the Maclaurin polynomial will cover the entire graph of cosine of x. This is how your calculator actually calculates the sine, cosine of values that are, not values that we just know, where we know the ratio of sides of pi over 3, 30, 60, 90 triangles, 45, 45, 90 triangles, like the sine of 2. What are the ratios of the sides? The calculator doesn't know the right triangle that is created when you talk about an angle of 2 radians. Okay? What the calculator does, and Texas Instruments probably created some sort of, algorithm, is they use a Taylor polynomial. They use a Maclaurin polynomial. They use this with a certain amount of terms. They probably will take a larger value, divide it by 2 pi to figure out where it is on a certain location. And then they know if they use just enough of these terms, they could find the sine or the cosine of any just random value. Not that your calculator does magic. It's not that the calculator has all of these values programmed in. It uses math, and it uses concepts like this. Understanding this is an equality. Not going to use an infinite amount of terms, but rather it'll use enough terms for a certain interval, and it'll take, other terms and move them over to that interval, and boom, they'll give you an answer that is accurate to the whatever decimal place. Okay? So, fantastic. For any value, we can use the Maclaurin polynomial for sine, cosine, and e. But let's look at 1 over 1 minus x. And if I start doing that, and why don't you guys start doing that because we do have some time. Why don't you graph 1 over 1 minus x and start adding terms. So the Maclaurin polynomial for 1 over 1 minus x is 1 plus x squared plus x cubed plus x to the 4th, okay? Just continue to add terms. What happens in this situation when you continue to add terms? All right, what do we notice? So here is 1 over 1 minus x, and here's the graph of my polynomial right here in purple. Okay, this is horrible. Not what I wanted. It's probably better in your calculator, but let's see. We kind of see it does a good job, but after around 0.5, it kind of goes off of it. And like before, we know that the 1 over 1 minus x is trending towards 0, and this is my polynomial. It does not cover the bottom half of things. We're only on the top half of things, and we're only here. Let's add more terms. I'm going to get to an even power, an odd power. Okay, we have an odd power, so the end behavior looks like this, but I see that I'm a little bit further, but I still am not getting the right half of things, and it doesn't look like I'm expanding that much quicker. Do we notice that? And how far did we go up to? X to the 11th, 12th, 13th, 14th? we don't see this beautiful picture of one thing laying on top of the other thing as much. Okay, why is that? And if you look at this kind of demonstration, they do a good job on the Wikipedia page. We can see here, e to the x. This is e to the x, and it's Taylor polynomial for 3 terms, 4 terms, 5 terms, 6 terms. We can see that it's covering more and more of the graph. Okay. Here, this is sine. This is sine x, and this is the 1st degree, and then the 3rd degree, the 5th degree, and they go to the 13th degree. And you notice how like the yellow, then the blue, then the pink goes further and further along the graph, okay, depending on the number of terms that we have, right? But then we look at this guy. Now this is the log of 1 plus x, which is related to 1 over 1 minus x. And we can see that as we're adding terms, we are not fitting along more and more of the curve. Rather, we are going sharper into a starting point, and they were going sharper from a starting point. So 20 terms, 45, 100. We don't go more and more along the graph, right? Which is kind of like different from what we saw with sine. Why is that? Well, let's look at the series. And let's look at the convergence of this series. If I plug in something like 1, and I have 1 plus 1 plus 1 plus 1 plus 1, does that converge to a value? No, that's going to trend towards infinity. If I plug in 2, so if I'm looking when x equals 2, 1 plus 2 plus 4 plus 8, is that going to converge to value? No, that's going to trend towards infinity. That's what you see happening in this situation. That when I start plugging in values greater than 1, all of a sudden when you start seeing if we're adding more and more terms, the quicker and quicker we're going to get to infinity. Does that make sense? Okay, well here, using the ratio test or understanding that this is a general form for a geometric series, we know that things only converge to values when r is less than 1 or greater than negative 1. Using the ratio test, we see that x has to be less than 1 with the endpoints being divergent. So plugging in 1 would get infinity, plugging in negative 1 would equal infinity. This means that for this series, 1 over 1 minus x, and it's Maclaurin polynomial 1 plus x squared, it will only equal each other when x is between negative 1 and 1. This makes sense. Think about a geometric series. We know this geometric series converges when r, the absolute value of r, is less than 1. And not only does it converge, we know what its sum is, 1 over 1 minus r. It's just the same deal. Okay? So here the Maclaurin polynomial doesn't help give us any value for 1 over 1 minus x. It'll only give us the values for 1 over 1 minus x between negative 1 and 1, which makes sense because geometric series will only approach a value if we have this r being between negative 1 and 1. Okay? So just interesting things about Taylor polynomials, that certain intervals sometimes are going to be constrained. We're not going to be able to use it to approximate any function value. But then, for certain polynomials like e to the x, sine, cosine, no, we can use its Maclaurin polynomial for any value of it, which is great. Okay? Now, knowing this is going to, and this brings us to our lesson pretty much today. Now, this was part of the lesson, understanding that the series the Maclaurin series creates this equality with this very tough function, but what we can use this to do is to write tougher Maclaurin series or Maclaurin polynomials, using the fact that f of x, frustrating, using the fact that f of x, I'll write f of x right to the left of e to the x, which equals e to the x, is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus on and on and on. And we could say plus x to the n over n factorial. Let's say I want to write a Maclaurin polynomial for e to the 2x. Gosh, why are you doing this? Okay. So f of x equals e to the x. Now, for your quiz today, you would have to take the derivatives of e to the 2x, like you did for your quiz today. Right? And you take the derivatives and you plug it into your Taylor polynomial formula, right? But I know e equals this. I know the function f of x equals this, which equals this. Well, what if I wanted to know f of 2x? Well, that's equal to e to the 2x, right? So if I, instead of have x, I have f of 2x. Well, that would be e to the 2x, which means that would equal this with just 2x plugged in everywhere. I don't need derivatives of derivatives of derivatives of derivatives. I can use a composition. F of 2x, which equals e to the 2x, will equal just 1 plus 2x plugged in for x, plus 2x squared over 2 factorial, plus 2x cubed over 3 factorial, plus 2x to the n over n factorial. Isn't that nice? Isn't that a lot easier than taking the derivative of the derivative of the derivative of the derivative? Looks a lot nicer. You would get the same answer regardless of how you do it. If you wanted to simplify this, you could. And you can simplify these terms, these coefficients as well. 4 over 2 is 2. 8 over 3 times 2 times 1 is 8 divided by 2, 4 over 3, et cetera, et cetera. That's nice. Okay. Well, let's say I want to find the Maclaurin polynomial or the Maclaurin series for sine of x squared. Well, before today, if I asked you to do this, you'd have to take derivatives of sine of x squared. And then the derivative of sine of x squared would be cos x squared times 2x. And that's how you'd find the first derivative of 0. And then to get that derivative, the second derivative, you'd have to use the product rule of the first derivative of sine of x squared, right? And then that's going to be complicated. This is just like question number 10 from your free response. I'll show you, we're going to get to 10 from your free response. So I know, though, now that sine of x is equal to its Maclaurin polynomial, which is x minus, and these need to be memorized, / understood and known. Well, now instead of doing all that work, just do the composition. Wherever you have x, plug in an x squared. I'm just finding f of x squared. That equals sine of x squared. Plug in an x squared. Okay? This works for derivatives and antiderivatives. Let's say we have sine of x squared. Write the Taylor series for f prime of x, which is equal to cos of x squared times 2x. Well, cos of x squared times 2x is the derivative of sine of x squared. If I want to, and I probably should write a simpler version here. This is x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial. Watch what I can do here. X squared to the 2n plus 1, you can multiply 2n plus 1 times 2, and you get that easy general form just by doing that simple exponent manipulation. X to the 4n plus 2 over 2n plus 1 factorial. Okay, cool. Well, f prime of x, just take the derivative of this function. 2x minus 6x to the 5th over 3 factorial plus 10x to the 9th over 5 factorial minus 14x to the 13th over 7 factorial. What if I asked you for big F of x? Now this is where, like, I don't know how to take the antiderivative of sine of x squared. I do not know what this antiderivative is. I don't think you can know. Maybe there's some technique to do. But I do know a polynomial that is equal to sine of x squared. And since I know sine of x squared equals this polynomial, I can say big F of x, the antiderivative of sine of x squared, will just be equal to the antiderivative of this polynomial. I can take the antiderivative of all of those individual pieces. Ready? It's just 1/3 x cubed, just the antiderivative of that, minus x to the 7th times 1/7 times 3 factorial. Keep going. Okay? The equality enables us to do this. The fact that the polynomial is not just a good approximation, but when the polynomial turns into a series and it's an infinite sum, it turns into equality, turns into being equal to each other. These aren't compositions. Sine of x over x is not a composition. But if I ask you to write like the Taylor series for sine of x over x around centered at x equals 0, it wouldn't be x equals 0, but yeah, whatever. I mean, you wouldn't be able to find the function value, but disregard. Don't worry about that. Like taking derivatives of this are tricky. You have to use the quotient rule, and then you'd have to use the quotient rule again. Tough stuff to do. Instead, I know sine of x equals its Maclaurin polynomial. Well, divide this by x. It's the same as taking this and multiplying that by 1 over x. You now can create an expression for sine x over x of the Taylor series for sine x over x by taking all of these terms and dividing it by x. Okay, and you can even simplify the general term if you'd like. So the general term, I just moved the x to be in the denominator. So here it is right here. And then if I wanted to simplify, I could rewrite x to the 2n plus 1 as x to the 2n times x divided by x. X's cancel, and there you have a general term, 1 minus x squared over 2 factorial plus x to the 4th over 5 factorial, et cetera, et cetera. Sorry, this should be a 3. Okay, you guys do the next one. Please write the first 4 terms and the nth term for the Taylor series about x equals 0 for x cubed cos x. You should be able to create the Maclaurin series for cosine of x pretty much just right off the bat. What I think of is that sine, cosine, e to the x are all very similar. E to the x includes all the terms they're all adding. Sine and cosine, since its derivatives alternate in signs, okay, so I know they're going to alternate in sign. And then I just think, okay, every other derivative is a 0, so I'm skipping every other term. It's all about which term do I start at. Do I start at 1 or do I start at x? Well, cosine of 0, the function value is 1. That's showing me I start out at 1 for this guy. Okay, go ahead and do this one. Write the first 4 terms and the nth term for the Taylor series for cos x times x cubed. Keep changing the factorials because I'm used to it. Any questions about this? I wrote as x to the 2n plus 3 because I just combined the x to the 2n times x cubed. Using your exponent properties, boom, you can write it as x to the 2n plus 3. Good so far. Okay, so compositions, multiplying things together, all can be done simply because of the equality of sine, cosine, e to the x and its Maclaurin series. Let's look at this one. write the first 4 terms of the Taylor series for this. Okay. Well, I know what the sine series is. Just going to stop there. I know what 1 over 1 minus x is. I'm just going to stop there. What should I do with both of these so that I can have sine x over 1 minus x? You're going to multiply them. I need to take this and multiply it by that, which means I'm going to be taking these terms assuming they go on forever and ever and ever, and multiply these terms by those terms. What type of multiplication needs to be done? Essentially like a foiling, a distributing. I know. It's a lot of distributing, right? It's an infinite amount of terms times an infinite amount of terms. Well, I only want just the first 4 terms, okay? And we know that our Taylor polynomials just increase by their exponents. So I just want the first 4 smallest degree terms. Well, how am I going to get that? Let's just start distributing these into all of these, because like 1 times x, that's going to be my lowest degree term no matter what. So I'm multiplying 1 by everything, and I get x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Okay? So those are terms that I get from adding 1. I can include a couple others, and I might have to. Now, I'm going to look at x to the first power here. And if I have the times x terms, I'll have an x squared minus an x to the 4th over 3 factorial plus an x to the 6th over 5 factorial. And I'm just going to stop there. If I look at the x squared terms, I'll have x cubed minus x to the 5th over 3 factorial. And I know I'm already going to be beyond that, x to the 7th over 5 factorial. So I got some x's, I got an x squared, I got some x cubes. Can I get another x to the 4th? There, x cubed. I multiply the x cubes, I have x cubed times x, and that's x to the 4th, minus the x cubed times the negative x cubed over 3 factorial would be x to the 6th over 3 factorial. Okay, I'm just going to stop there. Now we can start combining our like terms, and we can see that I'll have an x. I just have one of those. I have an x squared. Then I have this x cubed and this x cubed. So 3 times 2, that's going to be 6. So I have an x cubed minus an x cubed over 6. So that would be 5/6 of an x cubed. Next would be my x to the 4th powers. What do I have those? Well, I got one right here, and I have one right there. So x to the 4th over 3 factorial, that's x to the 4th over 6. I have an x to the 4th minus an x to the 4th over 6, and again, I get 5/6 x to the 4th. And those are my first 4 terms. It's kind of how these need to be done. They're fairly tricky, but just keep track of your foiling and you'll be okay. Moving on to other different types of problems. I want to get through these 3 problems. And there's a lot of different trickier types of problems. Your homework is fairly lengthy, but the answer key will be online. It involves these compositions as well as these kind of extra tricky problems. Okay? And this more of these problems deal with the knowledge of the formula for a nth term of a Taylor polynomial. Example. We have p of x is the 3rd degree Taylor polynomial for f about x equals 0. What is f to the 3rd of 0? First thing to do is to translate as this is the 3rd derivative of f at 0. Just get through this problem, and then I'm going to keep talking. You guys can go if you need to go. Okay? 3rd derivative of f at 0. Well, I know that the 3rd degree term of a Taylor polynomial is the following. The 3rd derivative at 0 times x cubed over 3 factorial. Knowing my Taylor polynomial formula, Maclaurin polynomial formula. I get that. Well, we say that has to be equal to this term here, because this is my 3rd degree Taylor polynomial. That term right there is negative 6x cubed. We can solve this for the 3rd derivative at 0. And I get that. Okay. You guys can head out. This is the next problem. I have a 2nd derivative. What is the coefficient of the 3rd degree term, the x cubed term? Again, this is what it would look like. Here, though, we're not looking for the 3rd derivative. We're looking for the coefficient of the x cubed term. So the coefficient is this entire thing. I can find the 3rd derivative, and the 3rd derivative at 0. So this is going to be 6 over 3 factorial times x cubed. What is the coefficient? 6 over 3 factorial, which is just 1. Okay, so asking for the nth derivative, a specific derivative, a specific coefficient. Let's look at the next problem. The nth derivative is given by this. What is the coefficient of x to the 4th term? So again, they're looking for the coefficient, so that's both the 4th derivative at 0 and then divided by the 4 factorial, which goes into the Maclaurin polynomial. They're looking for the coefficient, so I'm going to provide this information, and that is the coefficient. I will use this, which is an expression of the nth derivative, to find the 4th derivative. 4 plus 2, that gives me a 6. 4 plus 3, that's 7. 2 to the 4th is 16. So this is 6 over 7 times 2 to the 4th. I'm not even going to simplify that. So plugging that in here, my coefficient would be 6 over 7 times 2 to the 4th over 4 factorial. And I'm sure we could simplify that, but sometimes it's not important. And there is my answer. There's the coefficient to the x to the 4th term of the Maclaurin series. Okay, make sure you do those homework problems and look at the key.